So continuing on, we are going to look now at what is called a logarithm. And you can see the word logarithm, like if you take a look here, this again comes from your textbook. You see the word log here showing up. That is short for logarithm. It's a fun word to say. Logarithm, logarithm, logarithm. So give it a practice. So take a moment to read through this, and then we'll discuss in a bit. So quick pause, unpause when you're ready to move on. So this particular sort of, it calls it here an ancient puzzle. I'm going to refer to it rather as a type of problem that people simply needed to address. And so different cultures across time have found ways to do this. Until computers came around, it was all done with books and tables and very, very tedious calculations. But let's take a look here at these 1, 2, 3, 4 cases and see if we can figure out what's going on. So there's a relationship here between the 2, the 8, and the 3. It's the same relationship between the 3, the 27, and the 3, between the 5, the 25, and the 2, and between the 10, the 10,000, and the 4. Now, take this seriously. I do want you now to do a little pause, get a calculator, do some experimentation, and see if you can find a way to put these numbers together. You better have done a pause and done some investigation, or else I'm very, very disappointed in you. All right, let's see if maybe you came up with something similar to what I did. So if I'm looking for a way to put together the 2, the 8, and the 3, I'm going to remember what we just talked about here in the previous case. We were looking at how exponents work. Well, this is from the exact same section, so probably exponents are going to be involved again. So do a little bit of experimentation, and I hope you can figure out pretty quickly that, well, okay, so 2 to the power of 8 isn't 3. 8 to the power of 2 isn't 3. 2 to the power of 3, 2 to the power of 3 is 8. So if I take a 2 and then use this number as the exponent, I'm ending up with what was in these parentheses here inside the logarithm. Now, just some notation. This 2 is called the base of the logarithm, and it's written a little smaller and a little lower. The 8 is referred to as being inside the logarithm. So the way you say this is log base 2 of 8 is 3. Let's see if the same relationship holds over here. So we had this kind of pattern going on. 2 to the power of 3 gave us 8. So over here, is the same thing true? Is 3 to the power of 3 equal to 27? 3 times 3 times 3 is 27. Let's check here. Is 5 to the power of 2 equal to 25? Yes, it is. Okay, I think we've got things figured out. Just a final check here. Is 10 to the power of 4 equal to 10,000? Yes, it is. The nice thing about powers of 10 is that you just count zeros by what the power is. So 10 to the 4th is just a 1 with 4 zeros. Okay, now, once again, I'm going to ask you to do a little pause as you try and now solve for the missing pieces in these puzzles. And I'm going to leave this here up to you. So you can do them all at once, or you can do them and check them one at a time, whatever makes you happiest. So quick pause on the first, unpause when you're ready to check. So this time what's missing is the number over here. This number over here is the exponent. So the question is, 2 to what power gives us 16? Well, 2 to the first is 2, 2 to the second is 4, times 2 again, times 2 again. Okay, so 2 to the 1, 2, 3, 4. The question mark this time is the number 4. If you're missing the number on this side, you're looking for the exponent that you put on this 2 to get the 16. Next one. So got that mark there I didn't want. This time again, we're missing the exponent. So let's continue our list. It's still base 2. So 2, 4, 8, multiply by 2 again, we get 32. Okay, so this time I need an exponent of 5 to make that happen. And just do a quick check. Hop over here to your calculator. Is 2 to the power of 5 actually 32? Yeah, we've done good. Over here, this time what we're missing is the base number. So what number to the second power gives us 100. A couple of ways to do this. Probably the easiest is just to know that 100 to the second, or 10 to the second power is 100. You could also, to get rid of that exponent of 2, do a square root on both sides, and the square root of 100 does give you 10. So in this case, I want a 10 to be that question mark number. This one's probably the most straightforward. Not a whole lot of puzzling going on here. Take this base number 5, raise it to the power of 3, the number on the other side, that's your exponent. So 5 times 5 times 5 is 125. I don't expect you to have that memorized, but at least know how to calculate it quickly. Here, once again, we're missing that base number. So what number to the 4th power gives us 81? If you know it, great. If you don't, the way you get rid of a 4th power is with a 4th root. So if I come over here now and do a 4th root of 81, and forgive me, I'm going to type it as a fractional exponent. So I did that just to save myself a little time. A 1/4 power is the same thing as a 4th root, and I notice that it's giving me 3. So this time, I'm claiming that 3 to the 4th power is 81. So let's just make sure that actually works. Is 3 to the power of 4 equal to 81? Yes, awesome. And then lastly, 100 to what power gives us 10? Notice this time that the number got smaller. So it's not going to be a whole number power that makes this happen. So instead, I need to think about the relationship between 100 and 10. And in terms of powers and roots, 10 is the square root of 100. Well, think about that discussion we just had. When we did a 4th root, it was the same as a 1/4 power. So a square root is the same as a 1/2 power. Let's just check that real quick. Come over here to my calculator. I'm going to clear some things out. Is 100 to the power of 1/2 equal to 10? Sure enough, it is. Okay, we are in good shape there. So this ancient puzzle, as it's called, is just a way to define what the inverse of an exponential is. Notice that back here, we didn't actually give it a name. Here now, we are calling it something. So how is this ancient puzzle related to the inverse? It's giving us a name for this inverse. How can we use this idea to write the inverse in y equals form? Well, let's take a look at, how about this first case right here? 2 to the 3rd equals 8. So what we're essentially saying is I'm using a base of 2, and the y that I get out is equal to 2 when raised to the power that I choose to pick. So instead of a specifically 3 and 8, in general, the input we're calling x and the output we're calling y. Think of this as your original function. For our example here, we had a base of 3, same idea. So y equals 3 to the x, same process. How can we write the inverse starting with a y equals? Well, come up here. Notice that for the inverse, I need the x and the y to switch. So really, what I really want to do is to get the exponent by itself. That's what this logarithm does. It gets the exponent by itself. We use the word log. The base of the logarithm, in this case, it was 2. So in our case, we're going to use a 3 instead. And then what goes inside the logarithm should just be whatever our original result was. So when we inverse, we're getting that x as that original result. So what happens is we put an x. I'm going to put parentheses here. So y equals log base 3 of x. This is how you can write the inverse function of y equals 3 to the power of x. So, thing to take away from here. This notation is used to denote the inverse of an exponential function. The result, the output of a logarithm, is the exponent. It answers this question. What exponent do I need to put on this base number to get this number that's inside the logarithm? This statement here means the same thing as this statement here. What exponent do I put on b to get n? Well, if it's k, then b to the k power equals n. And this is tying up our discussion of inverses now. So y equals b to the x has an inverse of y equals log base b of x. So just like add and subtract undo each other, exponentials and logarithms undo each other.